Intermolecular forces are the forces that hold condensed states together, so liquids or solids are held together by intermolecular forces. The physical properties of a substance, such as density, melting point, boiling point, things like that, generally depend on the spacing between the particles that make up the substance. But what is determining that spacing is actually the forces of attraction among the particles of that substance. If we have stronger forces, it's going to be a higher density. There's also going to be a higher melting point and boiling point, which then would lead to the fact that it's more likely to be solid or liquid at room temperature as opposed to gas. This is very important. The average kinetic energy for all substances at the same temperature is the same. So room temperature is about 20 degrees Celsius. In a room at 20 degrees Celsius, you have solids, liquids, and gases all present, and they all have the same amount of energy. So it's not the temperature that determines the phase of something. It is actually the intermolecular forces, because the intermolecular forces are what determine a substance's melting point and boiling point. And that's what determines a substance's phase at a particular temperature. So oxygen is a gas at room temperature because oxygen has a very, very low boiling point because of the forces involved in holding oxygen molecules to other oxygen molecules. Water is a liquid at room temperature because its room temperature is in between its melting point and its boiling point. So inter means between or among. So intermolecular forces can hold together identical particles or two different types of particles. So it can be like water molecule to water molecule, that's an intermolecular force, or water molecule to a glass molecule in the instance of forming a meniscus. So it could be two of the same molecules, or it could be two different molecules. But what's important is that you understand that they are different than intramolecular forces, which are bonds. So intramolecular forces are what hold the hydrogen and oxygen together in a water molecule, whereas intermolecular forces are what hold one water molecule to another water molecule. So I'm going to illustrate that on this page. So I'm going to just try to color code some water molecules here. Let's flip that line upside down. And so I will make the bonds, the intramolecular forces, red. So these are the covalent bonds that we know of from last chapter. So this is an intra with an A, molecular force. This is an intramolecular force called a covalent bond. We know in water that the oxygens are partially negative and the hydrogens are partially positive. So it makes sense that the partial negative oxygen of one water molecule is attracted to the partial positive hydrogen of another water molecule. And so I will make that green. That's attracted to that, that one's attracted to that, that one's attracted to that. And so that is your intermolecular force. This one is called a hydrogen bond. So the forces holding the water molecule together itself are much stronger than the forces holding water molecule to water molecule. If I was to list the forces in order from weakest to strongest, our weakest force is called a dispersion force. And then after that is a dipole-dipole force. And then after that is hydrogen bond. And again, these are your molecular forces. And then after hydrogen bond, the next strongest force is a covalent bond. And then an ionic bond. And those are your intra with an A. intramolecular forces. Now, this is really the last time I will mention covalent bonds, because covalent bonds are not what determines something's state or its melting point or its boiling point or its viscosity or anything like that. It's more these attractions between positive particles and negative particles, so your intermolecular forces, and then, of course, ionic bonds as well. So dispersion forces occur in all substances. That is important to note, because dispersion forces happen really just from random movements of electrons. Everything has electrons, so everything's going to have some dispersion forces. Dispersion forces are the weakest forces. They are very short-lived. They are the only intermolecular force nonpolar molecules experience. So that is important as well, but please don't get that confused with, all particles do experience dispersion forces, but it is the only force that nonpolar molecules will experience. This is why nonpolar molecules, very oftentimes, smaller, lighter ones, are gases at room temperature, because they do not have strong forces holding particles together. So what happens in a dispersion force is atoms develop a temporary dipole, as electrons move around the nucleus. And then it's sometimes called temporary dipole, it could be called an instantaneous dipole, and what it can do is it can then induce a similar dipole in a neighboring atom. So you might even hear it referred to as an induced dipole. So what's happening in dispersion forces, if I look at the top of this picture from frame 1 to frame 3, this is a hydrogen atom, has 2 electrons, and you can see the electrons are just kind of randomly moving around until in frame 3, they just randomly happen to end up on the left side of the atom there, thus creating a partial negative charge on the left side of the atom and a partial positive charge on the right side of the atom. If that hydrogen atom then got close, so this in frame 3 is this one, then got close to another hydrogen atom, what it can do is that partial positive end can actually attract the electrons of a second hydrogen atom, thus inducing a dipole on that hydrogen atom, pulling the electrons to that side, creating that partial negative. And then, as we know, partial positive attracted to partial negative, that's a force that's going to hold those particles together. Dispersion forces become stronger as the size of the molecules or the atoms increase. You can think of size as molar mass. You can think of size as number of electrons. It all basically means the same thing. I'll even mass / E minus. So if I look at this table here with my noble gases, we know as we go down a group, atoms get bigger because we are adding energy levels. There's more electrons. There is a higher molar mass, all that stuff. So as you go from helium to neon to argon, so on and so forth, look at what happens to the boiling point. Helium's boiling point, 4.2 Kelvin, very, very, very low. Neon, a little bit higher, argon, a little bit higher, all the way up to xenon, 165 Kelvin, which is not very high. But it is much, 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 much higher than the boiling point of 4.2 Kelvin of helium. You can also see this trend of dispersion forces becoming stronger when we look at our halogens. We know the halogens make diatomics. So these are diatomic molecules, fluorine, chlorine, bromine, and iodine. And up at the top, we have small molecules. Going down to the bottom, we have big molecules. And at room temperature, that's important to note, at room temperature, fluorine and chlorine are both gas. Bromine is a liquid, and iodine is actually a solid. Now, these are all nonpolar molecules. So the only difference between like the fluorine, which is a gas at room temperature, and the iodine, which is a solid at room temperature, is that iodine is much bigger. So iodine has much stronger dispersion forces. Strong forces is going to make something solid. So going small to big also means we're going weak to strong with dispersion forces, only with dispersion forces. So Mr. Anderson is going to explain a little bit of that. Watch in the video what happens when he brings those 2 hydrogen atoms close together. And here he goes.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 16. It's on London dispersion forces, which were first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here. But before we move on and talk about it, think about the forces in this picture. Which are greater, the forces within the individual people holding their atoms together, or the forces between them holding them together in this photo? Well, clearly it's the forces within your body. And so this is the first video in a set of videos that talk about bonding between molecules and within molecules. And so if we think of them all as molecules and we move them apart a little bit, there are going to be the intermolecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular, within the molecule itself. And we'll talk more about those in later videos. The London dispersion forces are going to be attractive forces. These are intermolecular, between molecules. They're going to be found in all atoms and molecules. Everything is attracted through London dispersion forces. It's really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge, has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also, as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. So let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase is going to be these London dispersion forces. So right here I have two helium atoms, and so they're going to have two protons on the inside, two electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. So what this really is creating are two what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those two. It's fairly simple. It's going to hold them together. Now, it's just instantaneous. It's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres. And as a result, these ones are going to have more surface area, more contact area, so we're going to have greater forces. And so the boiling point of N-pentane is going to be higher than that of neopentane based on these London dispersion forces. What else? The polarizability. Polarizability, remember, is the squashiness. The more electrons we have, the more forces we're going to have. And so this right here is a protein. Proteins are massive in size, and a lot of that three-dimensional shape comes from these London dispersion forces. Also, it's going to explain why, as we go down in the periodic table, let's look at the halogens right here. Halogens are going to have the same valence electrons, but as we go to fluorine, chlorine, bromine, and iodine, we're actually going to go from gases, fluorine, chlorine, to liquid bromine, and then solid iodine. And that's all going to be based on these London dispersion forces. As the atoms get bigger, they have more electrons, we're going to have more of this uneven electrons. And then finally, pi bonding. That's where we're going to have orbitals.
We're not going to worry about pi bonding. All right, so dipole-dipole attraction is attraction between oppositely charged regions of polar molecules. These are stronger than dispersion forces because dispersion forces are temporary. They result from a temporary shift in electrons, whereas dipole-dipole forces, it is a permanent dipole. Classic HCl, right? We know there is a chlorine's more electronegative, so it has that partial negative. Hydrogen has that partial positive. We have the dipole moment going that way. And so if two HCl's get near each other, we know negative repels negative, negative attracts positive. So if there's another HCl, the negative Cl's will repel each other. The positive H is attracted to the negative Cl, and so they will kind of line up so that these negatives and positives match up, and then there's that attraction that's going to hold those molecules together. And again, this is stronger because it is a permanent dipole. It's always there, whereas in a dispersion force, it is temporary. Our last and strongest intermolecular force is a hydrogen bond. A hydrogen bond is a dipole-dipole attraction. That's very important for you to understand. It's just that it is a stronger dipole-dipole interaction. So there's not really any difference between a hydrogen bond and a dipole-dipole, other than hydrogen bond has to have a hydrogen bonded to fluorine, oxygen, or nitrogen. And it's fluorine, oxygen, and nitrogen because those are extremely electronegative. And so if you were asked, what's a more polar bond, HS or HN, you would say HN. This is where this hydrogen bonding then is coming in, because HN is a more polar bond. Those partial charges are stronger, so it's going to be a stronger attraction when you have something like that than when you have like an HS involved. And you can see the hydrogen bonds in water there. All right, so don't worry about that, and we're also not doing ion dipole, but this gives you a nice little summary of what kind of molecules or particles, I guess I should say, these forces are present in, a little depiction of what the force looks like, and then, your strength, it increases as you go down. So to answer this question, there's a few things going on here. What type of forces will be present in the liquid state of each of the following? What has the strongest forces? What has the weakest? So liquid state is specified because, again, gases do not experience intermolecular forces. So it has to be in the liquid state. It doesn't change what forces are present. It just, if it wasn't in the liquid state, there would be no forces present. If you need to draw the Lewis structures and draw the dipoles, then do it. So the first one here is one we haven't seen before. This is something called methanol. And so methanol looks like this. That OH is called a hydroxyl group in organic chemistry. It's what makes it an alcohol. That's why it's methanol. And so when I'm looking at this particle here, and I'm determining the polarity of it, yes, it does have a dipole moment right here, but it's just really that this little bit right there is polar. The rest of the molecule is actually nonpolar. It's just got that one little polar area with that OH. CO2, as we know, looks like this. And of course, the dipole moments go out and cancel each other. So I guess I should write this. So the methanol is polar. The CO2 is nonpolar. Water, we know. And again, you don't have to draw it if you know it offhand. Big dipole moment, polar. Krypton is just an atom by itself, so nonpolar. And then ammonia, NH3, is trigonal pyramid. So again, we do have a dipole moment going from the H to the N. So that's a polar molecule. So what types of forces are present? It's important to know if it's polar or nonpolar because that tells you what types of forces. Now, everything has dispersion forces, so they all have dispersion. But dispersion forces are the only forces that nonpolar molecules experience. So for the carbon dioxide and the krypton, that's it. That's all they have. Polar molecules also have dipole-dipole forces. So any polar molecule is going to have dipole-dipole. And then the last one we look for is hydrogen bond. Is hydrogen bonded to oxygen, fluorine, or nitrogen? And for this example, it actually so happens that, yes, they all also have hydrogen bonds. Now this says, what is the strongest? What is the weakest? So the weakest, we'll put it on that end. The strongest we'll put on this end. Overall, the weakest force is dispersion, but when I'm deciding between the krypton and the carbon dioxide, I have to take into account the molecule size. I have to take into account what Mr. Anderson was talking about, the contact area. Krypton is the weakest because it's just a single atom. So even though it has more mass and more electrons than carbon dioxide, it's just a single atom, whereas carbon dioxide is 3 atoms, so the krypton is the weakest. Carbon dioxide comes next, and now I have to decide between my methanol, my water, and my ammonia. Methanol is actually going to come next because again, methanol only has that one tiny little polar area, whereas in water and ammonia, the entire thing is polar. After that, fix that. I got to decide between ammonia and water. And so again, this goes back to what's a more polar bond? Is an NH bond more polar or is an OH bond more polar? An OH bond is more polar. There's a bigger electronegativity difference, and so that's going to be a stronger hydrogen bond. So it's actually going to go NH3 because that's a little bit weaker than the strong dipole in the water molecule. And then lastly, which of the following is most likely to be solid at room temperature? It's a really good idea to kind of restate these questions for yourself and say, okay, is this asking for strong forces or is this asking for weak forces? Most likely to be solid. Solid would mean there are strong forces in play here. So again, if you need to draw out the molecules, do so. SO3 is trigonal planar. It is nonpolar. BaO, that's metal nonmetal. That's actually ionic. HF is very, very strongly polar. And then O2, of course, is nonpolar. So most likely to be solid at room temperature, I'm looking for what is the strongest force. That's the ionic, the BaO. Of course, then followed by the HF, then the SO3, and then the O2.